development, everything else. So I've worked on autonomous projects for the military. I've done electric vehicles with different manufacturers at different standpoints at different times. So it was kind of a natural fit, although it was tough to give up a job with an Italian manufacturer where I had to spend at least a month or two in Italy test driving prototype motorcycles every year. But I told my family it was a sacrifice I was willing to give them. But I came into Local Motors not being very strong on the materials side, not knowing a lot about additive manufacturing as a whole. The fun part is, as I get into this, there's some startling things that start to happen. I've worked with the University of Tennessee with their civil engineering and their industrial engineering. I've been a guest lecturer at both. What additive manufacturing is going to do in the next few years is create a new discipline of engineering. If you have a Six Sigma 6, lean processes and controls, you can pretty much take that and throw it in the garbage if you apply additive manufacturing to the situation. Because it's a real easy math problem to figure out how many pounds of material you need to produce so much product. So there's no longer pre-predicated order times and things like that for on demand. So it's a very different type of manufacturing. It's a very different type of process. So I'm going to fast forward into Olli now. So we give you guys some scale here. When it comes to a vehicle manufacturer, it takes about 5 to 7 years to take a vehicle from an ideation, from a whiteboard project to an actual commercialized sort of vehicle platform. That's a normal cycle time for them, and it takes about $1 billion, roughly. So there's only been one manufacturer to date that has been able to produce enough vehicles in 1 year to offset the BOM of the development of the vehicle, and that's Hyundai. And they did it with the Elantra platform. They produced 227,000 vehicles in 1 year to completely erase the $1 billion development cost. Massive scales. Massive. So Olli was a design challenge, and the guy who actually designed it was a kid named Edgar Sorrento out of Cartagena, Colombia. He was a 22-year-old design student. I think it was in Italy at the time. Worked for a design house. We had a design challenge for Berlin for the mobility solution of the future for a very crowded, densely populated, narrow street Berlin. How do we solve it? So Olli came out of that. It was just an idea. Early 2016, we decided to make that a reality, and we said, let's do it. 90 days later, we produced 2 vehicles. That is a crazy time schedule. Additive manufacturing had a big part of that, and direct digital manufacturing specifically. So that's kind of how it birthed, and this is kind of where we've gone to. So we have Olli, your friendly mobility neighborhood solution. So what's the idea behind this? So it's a first mile, last mile solution standpoint. Meaning, if you wanted to ride the bus and it's a bit of a walk to the next bus stop, how do you get there? In order to understand that, they need a solution that takes you from your front door to the bus stop. And that would encourage people to ride the bus and use public transportation in a different manner. That's the last mile, first mile solution, meaning how do you get from the bus stop to your house, how do you get from your house to the bus stop. So you increase people's use of public transportation. That's really what we kind of focused on. There are a lot of iterations of that when we talk about last mile, first mile solutions, meaning to a train station, to a bus station, to a subway, to any type of interconnected mobility solution. We're making it easier for people to use that instead of getting in their car and choosing that transportation mode. And that's really what we're trying to focus on with this. So Olli is an NEV, the classification that we've set in, so it has a top speed of 25 miles an hour. And we're really looking at the more complicated issue. Everybody thinks about the Tesla, the highway cars, everything else. Teslas, everybody else is the driver assist. It is not an autonomous vehicle. Not close. It's just a help. You can't take your hands off the wheel. You can't watch Harry Potter. Bad things happen. It's not that smart of a system. So our sense was that if we tackle the more complicated urban environments, then the highway projects would be easier. Once we have the roadmap for that, it's kind of an easier solve. So in a low-speed environment, the risk is mitigated. Regulations are a little bit easier, and passenger safety is ultimately a lot better situation for everybody. So the way I basically describe it, anybody in here ridden in an autonomous vehicle? Nobody's ridden in an autonomous vehicle. Anybody been in an elevator? Guess what? It's an autonomous vehicle. The reality of what Olli is it's a horizontal elevator. It's not vertical. And that's what we're asking it to do. It's very boring. But the reality of it is it's meant to be. We want to take that part of your transit and make it palatable. If you don't have a steering wheel, we're control freaks. So if it's not a very smooth ride, like an elevator, if you've ever been in a very bumpy or jerky elevator, you remember that for a while. So the autonomous vehicle has to do the same thing. When you get an autonomous vehicle, it doesn't have a steering wheel. The ride conditions are predicated that it has to be smooth to create rider comfort and confidence in the system. So it's a really big part of what we work on. So that's kind of an overview shell shot of what it looks like, what it really is. So we kind of erase maybe some of the fantasy or confusion of what people might think it is. Olli's rollout development sort of standpoint is like this. Just like an elevator with stops, the original, as Olli's deployed within Knoxville and other areas, it's a predetermined, pre-route, predetermined stop situation, fixed stop. So it'll go around in a circle, could be 1.5 miles, 3 miles long, and it's going to make 5 or 6 stops within that to pick up and drop people off. As that system gets better, we feel confident in its abilities to do other things. We'll start initiating what we call waypoint, meaning that anyone within that loop could summon Olli and it would be able to stop at any point and drop you off at any point. You can predetermine that by a mobile app or by telling Olli through its what we're calling the AI conduit, meaning that it's talking to Alexa, Watson, whatever. So in that respect, you have some flexibility and you have the ability to be able to communicate with the vehicle and it can do more. The last step of that would be that we would give a predetermined area that could be 5 square blocks that Olli can operate in, kind of like an Uber. You can summon it, it'll pick you up and take you and drop you off anywhere within that square. And then as you add more Ollies to that situation, you suddenly start to see this linked system that allows you to give you coverage for an entire city. So how does it work? Multiple sensors, it sees what's around me. There's all sorts of different ways to think about this. And even our lovely team has vetted through 2 different types of autonomous systems, one being IDEO and one being what I'll call a CPU-based platform for the states. Both of those are very different. ECUs are kind of like your car. You have a body control module, you have an engine control module, you have a master ECU that actually manages and coordinates the communication pathways for all that. It's solid state, what I would call smart, linked together micro PLC, basically. So you're asking them to do a certain function, and then there's a master one that sits over the top of it that tells it the order of operation and how important it is in the operation of the whole vehicle. So like the one vehicle that we have in Europe has 8 ECUs, and it changes. As we add sensors, as we add technology to this, we have to add more ECU derivatives in order to control those types of sensors, and then determine the stack orientation in their order of importance. Meaning that something very close has a higher priority list than something that is seeing 300 yards down the road. So those are the types of things that we have to work through and understand. That the CPU-based system is a little bit different because of 2 things. There's only one manufacturer currently that has a CPU-based platform that will work in a vehicle. And the way I always describe this is, if you want to think about it like this, current CPUs don't work well in automobiles because it's like a CD player from the 1980s. Every time you hit a bump, it skips. Same things happen with the CPU. It's going to take time for that hardware development curve to get around because it takes a lot of CPU strength to be able to do this many types of calculations and the amount of data that can be generated from the amount of sensors that we have on the vehicle. Did I speak too quick? By the way, I'm from East Tennessee, so my bad. So where does that really go? What I'm saying is these vehicles, if I had 4 of them operating here in downtown Knoxville, in about a month, I could probably generate anywhere from 4 to 7 terabytes of data. It's an immense amount of data. A lot of it doesn't mean a lot, but the reality of it is that's the type of information that we're trying to process on a daily. And that's only what I would consider level 3.2 or level 3.4. We're not even at level 4. Level 5 is a totally different subject. So that's part of what we're working through. So when people ask me about autonomous vehicles, it's a very broad subject, and there's a lot of different issues that go along with it, but I work with the city. I work with the city engineering. Billy and I have worked with Omar and L, and we discuss all these types of subjects. We've talked with the Department of Transportation for Tennessee. How many people here knew that Tennessee passed legislation to allow platooning? That's a big deal for the autonomous world. So that means my little Olli bus there goes, oh, it only carries 12 people. If I daisy chain about 12 of them together, I get quite a few people in one shot. And they can operate a foot off each other's bumper. Tennessee's allowing us to do that now. So there's different subject matters. The vehicle's relevance in some respects is a point of price control. It is an expensive field to play in. But we want to make it flexible too, meaning that it can have multiple uses and purposes. If you went over to Thompson Boeing and they're operating Ollies instead of Ubers, they can operate in a daisy chain to take you to multiple parking lots that drop you off and daisy chain back together to pick up another group from the stadium and drop you back off again. That makes sense. But without those platooning laws and things like that, we can't do that. We can't even work on those capabilities. So working in the right environment, the right states, and the right municipalities makes a big difference in our ability to adapt and develop technologies. It can't just happen in a closed environment. The machines aren't the problem. Everybody else is. That's really what we're talking about. We can make all this stuff work in a closed environment all day long, but until you add the unpredictability of human traffic, that's where we really have to figure that out. So we talked about fixed route, waypoint on demand. This is where Olli starts to get interesting. Construction methodology, and we'll get into this in a little bit more detail. I want to skip a little bit here because of time. These are some of the partners that we work with as far as some of the bumper sensors, the LiDAR system, and so on and so forth. Does anybody know how LiDAR actually works and what we're actually doing with it? Does anybody think Google wants to make a car alphabet? They don't. It's not their goal. The LiDAR image of the United States is what they want. They're going around mapping and mapping and mapping and mapping, and they're going to sell that data back to the manufacturers of vehicles with a LiDAR map. The way we make this vehicle work is we go and we take a LiDAR and we go around and we do loops. We gather that data, then we take it back and we actually slice it back, and then we put a predicted roadway that we want the vehicle to stay within in that LiDAR map. And then we ask the vehicle to go around in that circle based off GPS, off of wheel count sensors, off of LMUs and other things. They predictably path it through that environment that we've mapped. And then it's comparing the data that it has from its map base to what the LiDAR is seeing currently. So that's how it's differentiating between what objects were there or are not there.
Are you guys the reason why I've seen a Google car around here?
Google's doing it anyway. They actively update their maps and they're actively doing their LiDAR situations all the time, and they're going to continue to do that again. For them,
I've seen two in the last month, so I didn't know.
Yeah, Tennessee's making it very attractive to be here now with the autonomous vehicle legislation that they passed. So that's a big part of that.
Where does Tennessee rank in regards to the other?
So there's 7 states that have enacted and understood and defined the 5 levels of autonomy. So you got 7 states that currently have legislation that allow the vehicles to operate, test, and develop and everything else and work within real environments. You have another 15 states that have what I would call committee level commitments to that. And then past that, I think there's 18 states that are in legislative meetings and subcommittees working on that. Issue we understand as a state, and it's a big deal to have the states make the determination. Level 5 autonomy is the vehicle can operate and do anything you can do at any time in any weather conditions, irregardless. That's the ultimate goal. Understanding those defined levels is what makes it easier for us to operate. But again, the states again have kind of battled over whether or not, California acted some. This is where I have fun with this. Everybody thinks California is ahead of everybody else with technology and everything else, but they're not. So they enacted some limited legislation to allow autonomous vehicles to test and develop in California. But then we have a vehicle like this, and one of the laws says that it has to have a steering wheel. Problem. So it can't do it. And so they had to go back and say, we'll make a caveat for this. And that caveat, the speed at which they moved was about 18 months before they even submitted it to a vote. It still hasn't passed.
So if it's autonomous, why is platooning necessary? I would think that it would queue itself up and it wouldn't need to follow another one if it's autonomous.
Well, platooning is an interesting situation when you talk about highway cars because it's a very different thing. They're going to platoon based off of distance to travel, distance to exit, and distance that they're going to try to be more efficient with gas or with electricity, taking advantage of of wind efficiencies, right? So that's a different idea. But the other side of it is, on the platooning side of it, when you're talking this size, when you're talking about a small mobility package like this, to be able to move large amounts of people, you need that type of legislation because we're going to operate them very close together. Current laws are written that you have to have reactionary gaps. When it comes to autonomous vehicles, if it has to be written by state law, we can't write in that it can actually get on another autonomous vehicle's rear end that closely, because that's breaking the law. So we have to write these laws that allow them to operate in the way that we want them to.
So it doesn't need a platoon for loading and unloading efficiency?
Correct.
Just when it's traveling?
Just when it's traveling. So that's the main reason we want to see those. Sensor ranges are predicated upon where we put them on the vehicle, what types of sensors we're using, and all that other fun stuff. Biggest thing I try to explain to people about autonomous vehicles and understanding limitations, if I took you in a really big warehouse and I gave you a really dim flashlight and told you to run from one end to the other and had 250,000 boxes in it, and said you cannot hit any of those boxes, I'm asking you to do the exact same thing an autonomous vehicle has to do. It's literally that complicated. So, there's a lot of different ideations of how we get past this and what we can do with it. There's different types of economies that start to come out of this type of transportation. All sorts of technology infusions and crossovers that we've never seen before that are happening. So it's a really interesting area to stand in. And again, we're working with that. Now, going back to what I just said about what does an autonomous vehicle see? This is what it sees. It has to make a decision left or right. I mean, if you're pre-predicated on the route that it has to go down, or it has to make some sort of decision. It's very complicated when you have a short range to make that decision. Everybody loves to bring this up. Who does it hit, the old people or the young people? Everybody thinks this is an ethical question. And it is. If you do it right, it sees this. It knows where everybody is all the time. It's not a decision you're going to make. The vehicle is going to know a half mile before it gets there that the old people were walking towards that intersection and have had a tendency not to pay attention to where they're crossing, or vice versa. It's about using environmental sensors to allow the vehicles to see more than they can now, because we get the same information. I know in my neighborhood where kids love to run across the street, I always slow down through there. There's days I want to go faster, but that's another story.
Are those sensors static, or are each one of those always communicating with each other, letting know what its environment is?
Well, currently that's kind of the question. And when I say it's kind of the question, the federal government says that I have to report so many points of data, I have to do all these other wonderful things. Communication to vehicle is a little bit more complicated because there's no set standard. The OEs that Billy and I talk with all the time, what was the last response we got? We're waiting for the FCC to tell us how to do it. So that's the fun part, right? So you're talking about a burgeoning technology that nobody's written the rules for yet.
Has the government plan on adapting the environment as well?
They're going to have to in some form or fashion, right? So that's kind of a bigger question that we work on constantly, and we work with our partners to try to understand. Because just like when I go out and I talk to clients or whatever, again, how did I engineer up as a salesman, but whatever, it's still the same problem for me. It is a technical challenge to deploy the vehicle in any environment we go to, and everyone's going to be different. Even when we talk about communication lines, there's some places that Verizon works really well. And there's a push for everybody to go to 5G. But if I go to South Texas, there's a problem with 5G. They're over pushing 4G so much the 5G bandwidth doesn't really work well, and there's a lot of what we call ambient noise that causes refractive issues that you can't get good communication lines. So that's a problem. And then we get into, if we're having to negotiate cell signals to communicate, to track, to do all these other things, what do cell phone providers do when you get to a bandwidth? I told you how much data I produce, 47 terabytes in a month. Can you imagine negotiating that contract for a cell phone bill? This would be ridiculous. So there's some of this that we have to ask, do we make sense, and are we doing this the right way, and how do we make these things work? Well, the problem is the cities and everybody else understand some of that. And so they're trying to be proactive, and they're doing things like $15 million LED lights and $30 million for running a fiber optic line around a certain part of the city to try to negotiate that. But they don't know how to tap it in, and the vehicle manufacturers haven't figured that part exactly yet either. So there's all that going on. It's like what I call this background noise of technologies trying to figure it out. And it's very interesting to watch.
Are they going for standardization versus?
I don't think, that's one of the things I don't think that They don't know what they don't know, and until somebody comes in and writes the roadmap, I've had to write, Billy's been part of this, where we've written recommendations for legislative ideas and guidance. So I wrote a grant for NYSERDA, which is the New York State. Out of 61 entrants, mine was the #1 chosen entry. That was our development mule to go to the University of Buffalo. But I wrote it in a standpoint that to develop these technologies in a controlled way with oversight and overview with multiple technologies to help them understand it was the right approach. Don't do highway, do slow speed, because you get more data a lot faster. So they liked that approach and they actually chose it, which was cool, a lot of work, but they're really asking us to tell them. And again, you know, in some spaces, I would say that's the right approach. Ask the experts to tell you what you don't know. So we're trying to help them come up with those guidelines to make it fair for everybody. I mean, we've worked with a lot of different manufacturers. Billy and I have sat in with VW, BMW, Ford, Chevrolet, Nissan, all these different manufacturers from all over the globe. And it's a very cooperative environment for the most part on this side, because we're all trying to get to the same space. And again, and I say cooperative because we're wanting to know, we all work together to try to help the legislators understand. So that's why it's a very cooperative environment currently. The integration part that I was just talking about is, this would be a typical sort of scenario for what I would call a traffic control center. And this is kind of what's going to happen on the oversight for autonomous vehicles. There'll be a control center on the background. We run 6 external cameras on Olli. We run 4 internal cameras or 2 internal cameras, depending on the configuration. And all that information has to come back from monitoring. If there's a problem, it may need to be looked at, to be an emergency situation, all those things. So it has to tie into the infrastructure somehow, in some way, in a way that's digestible. So we use back of house monitoring and things like that to connect to the transit authorities and whoever. So that's kind of how it sort of works. The integration part of this too, we are very fortunate in this environment, and it works very well for local motors. And part of the reason local motors is here, get back to 2 to 3 grand. Trust me. So this is where we're going. The partnerships in Oak Ridge, at NTRC, at MDF have been pivotal and a major reason why we came to KnoxData. For no other reason for that. This camera system that you're looking at right here, I'm working on a integration pack to work with us. This is GridSmart. They're just down the street from NTRC and MDF. Bill Malkis is a great guy. They have some interesting technology and do digital camera and traffic infrastructure monitoring better than anybody else globally. I'm telling you. They can predictively analyze the amount of vehicles in a lane. They can tell the difference between a tractor trailer and a car and predictably hold red lights longer to allow those traffics to go through faster and more speedy. The part where this gets interesting is if you start looking at it as the pathways, as our vehicles coming through, to give it better advantages, we do what we call a green wave that allows the vehicle to catch all the green lights. So we're timing the vehicle to catch all the green lights through a system so it's more efficient to travel on it than it would be to drive your own car. But working with these technology partners is how we figure that out. So that's just one of the integration pieces of the puzzle that we're always working on. The other side of it is, how did we get here, and what are we going to do with it? In a second. What does it really look like? What is the real use for this? We talked about last mile, first mile. Community and Seaside. Remote.
You think this is actually in use?
We went to the facilities and actually demoed it out, and we worked with them on this, and this is one of the concepts that we've been working on. You saw the kids go up and scan their phone, and then the part of that is I've been working on a security problem for ORNL for probably 5 months now. They have a huge problem with employee parking at some of the lab spaces, because you go in, You park, you got a half-mile hike over to where the trolley station is. Then they got a guy driving around in a van. If you get there at 4:30 in the morning, or before 4:30 in the morning, he's not running. At 4:30 they start. At 4 o'clock in the afternoon, they'll start the routes again. Some days, some not. And it's a big problem for them. And the other part of it is, if you're going in one secure labs, you have to take a clear backpack with your ID badge. You go up to a security gate, put all your stuff on the conveyor belt, they scan your stuff, you walk through a metal detector, show your ID, and you finally get to go into the building and go to work. Well, like this, where this sort of comes from, is the idea that we would put Olli shuttles in play. The employee would go up, scan his ID badge to open the door to even get in Olli. And every person that gets in has to scan the badge. The facial recognition features that we can do with the cameras will allow us to double check the ID of the person that was scanned with the person that steps in. There's a scanning locker that they put their stuff in that scans everything in. We lock them in and bypass all the security lines and take them straight to the door and drop them off because we've vetted them. That's a solution to a big problem. Cornell would love to put more staff on the outside of the perimeter to control outside security concerns as opposed to scanning all the employees' badges all day long. It's a complacent activity. There's a lot of error with it. There's a lot of things that is very problematic with it. And this is a very efficient way to show that. But the school kids is a very good approach to that as well. So we can lock kids in. We don't have bus drivers in. If you live in Knoxville, you know the bus accidents that we've had over the last 45 years. The majority of those are attributed to bus drivers being distracted in some form or fashion. This eliminates that. So in these types of environments, this is a very appropriate use of the technology. But again, it's still to come. So where do I come with this? Again, new markets, new services. But the thing about Olli, for its commercial success, is it has to be a very flexible platform. For me, the first Ollis were built in what I can consider a component fashion. We had a aluminum frame, some additive manufacturing parts and features on it, maybe not the best use of it. And then we went and did this. So I'm going to speak to this in just general terms because I come from the business side of things, and that's how I always drive things. Olli's ideation and the way it was originally started with what I call component building, started out with an aluminum frame, some additive manufacturing, was very laborious. We're talking about 300 to 400 hours of labor to get to the one that you saw driving down the street in that rolling chassis form. So we did the cost analysis, and our team here in Knoxville worked on this exclusively. And basically, we did the analysis. They asked me to run the numbers on it. So this is the way it works. $40,000, about 300 hours of labor time, and you come up with an aluminum hybrid composite system. This system is about 16 hours of assembly labor, roughly, we did some more picture, and about $8,500 worth of material and parts. And it took about 4 people to do that. This is where scale and scope split. To make money on the other side, I have to sell a lot, and I can start working the cost of the vehicles down by ordering lots of those pieces to be built, really, like thousands. And then I start getting these big order chunks and getting reductions in part costs. Here we have a base material, pelletized material that we use, and we start shrinking it down that way. And then the other side of it is that we came up with a different design technique that allowed quick assembly times and flexibility of design, meaning we could lengthen it, narrow it, shorten it, widen it, whatever we need to do in order to satisfy customer needs. So now we have a customizable, configurable vehicle because it's in a digital format. I've got one customer down in Florida that built a facility that's, I want to say they spent over $58 million on development. And they knew they wanted to do autonomous vehicles, but they built overpasses that were 8 feet tall. No manufacturer of an autonomous vehicle has a vehicle that will fit under that. But guess what? With that one, we can. Because we can bring the ceiling heights down. Because it's a digital format. That's where things go really haywire. We would never print shock absorbers or A-arms or things like that. Scale wins with small componentry. But when you take part reduction counts in this vehicle, and we went from 3,700 and some odd parts on the standardized vehicle and reduced them to about 173 for this, and that's talking about the little bolts and screws and all the little nuts and stuff that we put in some of the holders, that's a major difference. And that's where additive manufacturing really starts to show off what it can do. And why it's a big deal for manufacturing, why it's a big deal for commercial producers and everyone else that is looking into this space, why is it changing? The other part you have to remember is before we printed this guy, we printed, I think, 15 or 16 of the small models. It was exactly the same CAD file. I mean, literally, we changed it a little bit to scale it because there were some things we wanted for reinforcement, but it was the same file. And again, it starts on the small ones, starts at the maker size, but then it scales appropriately size-wise for the big printer. The same file, it doesn't matter. We slice it differently, but there's things that he'll get into that I'll sit back and let him do that explain most of that. But that's where we went. And that's what my clients want. That's what cities want. They want to see this. Why? It's recyclable, 98% recyclable. It's perfect. And it's flexible. The design's flexible. You know, we could start looking at the iterations that they want to come. Maybe they need it to carry more passengers. Maybe they need it smaller to fit in a tighter area. Whatever. That's where digital manufacturing and additive manufacturing start to really take over. Because just like when I sat with Ford, Nissan, and everybody else, I pointed out to them, I said 15 years ago, how many models were in your car line? I don't know. I was like, well, for Ford, it was 9, which was actually big. Chevrolet had 7. So how many do you have now? They were like, I was like 36. To hold market share, they're building more customized cars to certain market segments to hold on to it. And every manufacturer is branching out that way. So no one single line is the profit maker anymore. And this is where this starts to really start making sense, even for them. But where does Local Motors sit in that world? Reality is, we'll never be the big car manufacturer. It's not what we are. What we will be is a market-defining tool. They'll come to us and say, we've got an idea. We want you to build 1,000 of these vehicles because we think there's a good market for it. Well, you can make those at a low cost comparatively to us because there would never be enough, out of 1,000 units, it would never be enough of them to offset the BOM of development with their typical manufacturing side. But on this side, you can be profitable at it and validated in market space. So we're that in-between soft spot that allows them to push into new areas they haven't thought about yet. And that's what Local Motors really does. So I hope that somewhat explains how Olli came to be, what it is and what it isn't. And there's much more to the material science and to the development of the vehicle. And I'll turn this over to Charles.
Have you mind tested this thing? Have you gone around and done some loops and had somebody there ready to hit the stop button?
Billy spent more than enough time in it, and actually in that video you saw the vehicle actually responded to the guy. That wasn't us hitting the brake.
Yeah,
we were letting the sensors do that.
Yeah, we have object detection.
So
yeah, we've done a lot of testing.
We got that right.
Well, there was a couple of people we hoped, but it didn't.
So here we're trying to determine is it a soccer ball or a deer.
Right.
So think about it.
So if you really want to bore yourselves and you guys don't sleep at night, and I've read the majority of these studies, what is called LiDAR, object recognition, and it looks at whether things are symmetrical or not, and it's doing comparison data on symmetry, and it actually does a slice, a 50-50 slice of whatever it's actually saying to determine the symmetrical value of it, and then it's making determinations off of that. Again, if you want to bore yourself to sleep, you can read lots of research and develop material from those.
It seems to me that most accidents probably occur at intersections. Is there sensor technology built into Olli to do a crash, maybe speeding up if it senses a T-bone coming in at it or something like that? Or
Well, there is, and there
better
is.
than anything else?
There is and there isn't. And again, I'll let Charlie get into his in just a second, but I'll give you this a little bit. So if you have a four-way stop here in Knoxville, it's four-way stop sign. How many people stop at a four-way stop? Guess what? CDOT says nobody does. But we have to write rules for Olli that say you have to stop. And the rules of the road say that the person on the right has the right of way. The reality of it is we do what's called order of operation, meaning that if I come into the intersection, that guy was before me, I know he's going next and I'm not going after him. We'll have to understand about autonomous vehicles. We write by the rules of the law because we have to. But we have to give the vehicle the advantage to understand how to deal with that situation. So how would you deal with that? You would actually give Olli a camera at a four-way stop to allow it to know the order of operation before it ever got there, so it knows it's entering space, so it would actually be able to cope with that roll-through system.
Will Olli recognize this from my window?
It could. That's the sad
That's
part.
what happens at four-way stop.
Well, that's the fun part, because again, that's where we'll have to figure out some of that stuff, but again, without giving it the information beforehand, the waving in the hand or anything else wouldn't matter anyway, because it wouldn't even know if you were actually being a nice guy to give it the right of way.
Well, what about Olli communicating with the other drivers? Because that four-way stop, a lot of that, Board of Operations happens just from eye contact, you know, and knowing, okay, I know that you know, learn with a hand.
Yeah, you're right about that, but that's one of the other part of the software side of it. When we looked at the camera systems, one of the companies that I worked with was what's called an emotional recognition software base. So what they actually do is take people's face, they can scrub all the identifying features and get your emotional responses.
I mean, as far as Olli communicating back to the other drivers, like
Well,
if I'm at that four-way.
So I have a sign on top that will allow them to know what's up. So, you know, that's where we get into that fun part. It has to be a two-way street. How do you make that more intuitive? Then we need to get it more information.
But you're ignoring human error and human ignorance.
Yeah.
No, and that's where I also say, yes, I agree with you on that one, but that's the fun part of that. And it's one of the subject matters that I'm spending probably the most time on, is that there's a way to do that and give it all the foreknowledge so that you would know a mile and a half, 2 miles out, there's a guy coming in the opposite direction that shows a propensity of being drunk. We've already alerted the authorities to take the right-hand side and make a right-hand turn to avoid that issue. So those are the types of things you have to do.
It's a whole different thing. I mean, are you gonna put like Olli light posts in every car so that?
Not necessarily.
Olli gets there,
This is a slow development curve, and again, this is an ideation of working with multiple technology partners to figure out certain scenarios, and every environment's different. So we look at these use cases where we're going to be allowed to operate, and we're building to understand those environments, and each one's going to be different.
You're making social judgments as you go.
We have to. But everybody does when you get in the car.
Right. I mean, you've got to be able to do it right.
We do the same thing.
Like
but
profile.
Every one of us that's leaving, I mean, we're prone to make those mistakes too.
Everybody is, and again, you know, the fun part of this is more cars become automated and we get to the levels of autonomy get higher, then the propensity for accidents is going to go down when we take the human error factor out of the equation. So that's where it all starts to really, but the only way people are going to adapt to it is we make it convenient. Everybody gets out of their house, walks outside, there's a car in front of you, you get in the car and you go.
Well, I think the government is pushing that all vehicles, whether they're autonomous or not, in the future talk to each other.
Well, there's a 3-year plan, but you have to remember, if I legislate it in 3 years that every car has to have V2V technology, the problem with that is, even with V2V technology, meaning they can tell each other, I'm in your blind spot, I won't allow the car to go into it. The problem with V2V technology is, are you planning to buy a car in the next 5 years?
But I mean, the integration is working.
Well, and that's where it gets kind of funny. Even though they legislate it, doesn't mean the way that would impact would look, and it looks currently is, NHTSA and FMVSS both agree it's a 8 to 12 year plan before we'll have a 70% saturation, and that data is actually material. So that's the timeline, because everybody builds cars so much better than they used to. People keep their cars longer, which is why if you go look at the average used car mileage at this point, you can see, you know, 118, 120,000 mile vehicles getting, you know, $20,000 premiums for them because they're not worn out yet. So that means people are holding on to them a lot longer, and they're holding the residual value better. So that saturation of vehicles with good technology is going to take a while, and retrofitting them is another subject altogether. So it's just going to take time on that end of it. But that's why, again, I think working with cities and municipalities and governments and everybody else to make the environments better will help the vehicle development timeline go faster.
So I watched a 60 Minutes show, and they were talking about the technology. Yeah, it's not only thinking about now, but it's also going through scenarios of the future. What's this guy doing? You're at a stoplight. He can build different ways, and the computer's already thinking about that, whereas you wouldn't be.
Yeah, and again, you know, that's part of that what we call predictive analytics that we constantly work with. And again, there's environments that I'll tell you now that, you know, India will never see autonomous vehicles for 20 years. Why? Because their infrastructure is horrible. If you've ever gone there, if you've ever been to India, especially like Mumbai or Jakarta, one thing you learn, if somebody takes you there, don't stop when you walk across the street. The guys on scooters will pass you. If you stop, they will hit you every single time. And it's a tough world to kind of live in, but they have a system. There's a system to it, but it's not one machines can understand yet. It's too problematic. It's too chaotic. And it'll be time before they advance. As they build new cities, they're thinking about it. They're fixing that. the old cities are going to be the problem. Japan's no different. Japan has the same issues. Old cities are very problematic. The newer cities where they've gone and redone the roads and everything else, they're thinking about it and they're fixing it. US is no different in that respect as well. Sorry, my bad.
That's all right.
Go ahead, Charlie.
Okay, so I'm Charlie Hill. I'm advanced materials engineer with Locomotives, and I started my career at Air Force Research Laboratory in advanced composite materials, so more traditional laminate type composites. And then around 2000, I went to NASA Johnson Space Center and did more general materials and process support for shuttle and station. And then also any composite projects that we built in-house for those programs. And I want to mention my team here. Robert Betzel and Kyle Rowe are both, young PhDs, and they've really done most of the work, sort of running circles around me as we've done this development. And I put this presentation together in March, although I've added some new stuff, but it really goes through everything we've done through the 26 months that I've been with the company, and it's focused on materials development and the large-scale 3D printing. So as an overview, I'm going to talk about the motivational factors. Why would you want to 3D print a car? I'll talk about the extrusion deposition process, which is the large-scale 3D printing process. The baseline materials characterization, when we all started, the material that was being printed with, and then all the new materials that we've looked at since then, and then trying to develop an understanding of printability. What makes a material printable in this process? And then also, so how do we evaluate structurally how the material behaves in complex shapes, and the testing that we've done related to that. And then some initial structural analysis of the 3D printed Olli, and then details of that design. So why would you 3D print a car? And so originally we had this highway car program, and the vision was you could come into a microfactory, you could pick out a car design and have it printed over the next 2 or 3 days while you hung out there, and even maybe help put it together. And that's still a vision long term that we could be able to do that, but we've now focused on this one product. So it enables these rapid design and development cycles, like 3-month cycles. We predicted we could have a new design in the production. It enables this customer configuration and on-demand build capability. So you don't have to have this large inventory of product at the dealership. Basically, for the price of a dealership and inventory, you can have a microfactory and produce the cars as needed. Also, this is a thermoplastic composite material that's fully recyclable. So that's a very good for the environment. And the other advantage is crash performance. So thermoplastic composites are very good in crash performance. And so that's two of the plots here. One is the energy efficiency of the process. And this was taken from a DOE study of various traditional manufacturing processes and predicting what the energy efficiency as a function, their energy requirements as a function of process rate for the BAM process there, and it's highly efficient. And the second chart just shows the specific energy absorption of various materials. So if you look at like foam, honeycomb, steel, and aluminum, and then as you get into carbon fiber reinforced polymers and thermoplastics, they're just much better at energy absorption. So we should be able to build a lightweight vehicle that meets crash requirements using this material and process. So the extrusion deposition process, it's pretty simple when you first look at it. There's a pellet feed system and a single screw extruder with a 5-zone temperature control and an XYZ manipulator. So it just basically draws this the design layer by layer onto a heated bed. Now the hard part is dynamic speed control. So you're trying to deposit these layers, and it has to speed up and slow down. And so extrusion processes they're typically very steady state. Extruders are operated at steady state. So we're doing something very different when we're stopping and starting and slowing down and speeding up, and that's a real challenge to match the pump speed of the extruder to the speed of the speed that it's moving, and then maintain a constant feed width.
Somebody see who's making
So, you know, this was a partnership with Oak Ridge National Labs and Cincinnati Incorporated that manufactures this printer to produce the Strati, which was, they used a 20% carbon fiber reinforced ABS plastic. And that was really just the first material that worked in the process. ABS is very forgiving in the process. It has a wide processing window, so it worked very well. And we sort of inherited a design of experiments that was in process, and where they adjusted various process parameters, mainly the time between layers. So the longer it takes to print a layer, the cooler that material is, and the weaker that bond is between the layers. So we'll kind of look at that. Just looking at mechanical properties. So when we want to, when you design a structure, typically this is based on the Composite Materials Handbook approach, where you do coupon level testing to get your basic material properties, and then you just move up in complexity through elements and details and subcomponents, and then like full vehicle structural testing. And it's also showing the fatigue type testing that we do, and then the standard flat dog bone coupon that we use for tension testing. And we're also doing like creep and then environmental resistance, UV and creep type properties. So this sort of shows the carbon fiber ABS properties in the 3 different directions. So if I maybe go back and show that print direction. So X, Y, and Z. X is the direction that it's printing, the B direction, and it really aligns the fibers. About 90% of the fibers are aligned in that print direction. So you get much better properties, higher strength and modulus in that print direction. Versus within the layer, and then horizontal or perpendicular to that print direction. So you can see it's about 3 times both the strength and modulus in that X direction versus the Y and Z direction. And then you can also see, as a function of time between layers, here this shows 5 and 10 minutes between layers, so the strength drops as a function of time, and we've done some further studies with that.
Can you heat it up or go back to like a warm mold?
So yeah, there are we're working on a lot of different ideas about how to improve that layer adhesion. They've done studies with like a heat lamp type thing, but you want to print very fast. So in order to get enough heat into the material when you're moving that fast is a challenge. So that is being worked. There's a lot of different approaches to solve that problem. But when I first came in and I saw this structure, it has a lot of defects between the layers, I was very concerned about the fatigue performance. So one of the first things, beyond just this quasi-static tension type test, we did the fatigue testing. And so this just shows that data in X, Y, and Z direction. It shows the fracture type surfaces you get in fatigue. And then here I'm comparing it to conventional materials on a specific basis, so per unit mass. In the X direction, it's pretty close to like a low carbon steel, but in the Y and Z, that was pretty low in fatigue, and so we knew immediately we needed to do something to improve that performance. Either definitely looking at newer materials. We were immediately interested in nylon-based materials for better properties, as well as ways to reinforce it. So I'm going to talk about that a little bit. This is so looking at the details of the fiber and the looking at it under a microscope. The first was sort of just the optical microscope, looking at the the inside of the bead versus the outer layers of the bead, you can see there's a difference in fiber alignment. The fibers are more highly aligned in the outer surface of the bead. And then there's a new type of micro CT scan. So this is like a computer tomography, but on a very high resolution, up to micron resolution. And then we could see in various slices through the material, both the porosity, and this slice is taken like right between the layers, and it's showing in red the porosity there. So there's a lot of voids in between the layers that really contributes to that low interlaminar strength. And then also we get the more details of the fiber alignment. And then the plot here shows the fiber length. So the fiber length is also within a tight range. The process itself tends to break the fibers. So you may start with like a 6mm fiber when it's first compounded. So it goes through the compounded process to make the pellet, and that reduces it to like a millimeter. And then by the time it goes through the BAM, it gets reduced again to like a 200 to 300 micron fiber length. So the first thing, as a traditional composites person wanting to build a crash-worthy vehicle in 24 months, that was our original goal. I wanted to take that process, build a structure, and just overwrap it with continuous carbon fiber and resin infuse it. I was like, this is an immediate way we can build a really strong. And so we did this really as an experiment, and then we demonstrated it on what we call our construction mule. So the front section of a vehicle, you can see here like a front suspension that's mounted. This is just the printed part, but then we took it, we overwrapped it with carbon fiber, and then envelope back it and resin mounted on the vehicle. But this is sort of the analysis showing that it can take those driving loads, just a single layer of printed material once it's overwrapped with composite. And then the other idea was you could put metal inserts in there, and when you resin infuse it, it penetrates and bonds the metal to the composite. And but really we wanted to get in, we really didn't want to have to do that. There's a lot of extra labor involved. The vision was 3D print car. So the goal was really to find a better material. So we evaluated, at the time, this presentation, it was 60. We're probably at 70 different materials now that we've run through the BAM process and evaluated mechanically. Our typical test run will be, we'll print a hexagon of the material. It takes a little while to, when you put a new material in, you usually have set point temperatures from the manufacturer, so we'll run the initial set points, and if that works fine, then we'll have to dial in the bead width, so we get the initial RPMs and the print speed, and we'll print a hexagon. We take thermal data, so we use an IR camera, and we monitor those so that we get the cooling rate of the material during printing. We take notes on, there's a lot of qualitative aspects to printability. I'll show some photos of what can go wrong. And then we selected 12. We had a project with the Institute for Advanced Composite Manufacturing Innovation where we had like a certain fund amount of testing that we could do. So we had to select 12 for that, where we did rheology, which is the viscosity measurement, and TMA, which is thermal mechanical, or it gives you the CTE of the material. And then just did the X and Z direction tension tests.
I have a question for you. So a lot of times on 3D print forums, you'll see someone post a picture of their failure, and they'll say, what did I do wrong? What went wrong? And my first question is, were you watching it as it was printing? Because you talked about qualitative observations, and a lot of times you can see what it's doing if you just watch closely. Have you found that with your process too?
Definitely, definitely. I mean, we monitor all the prints, and you can see when things are going wrong, and we measure that bead width, and So it's very important, especially when you're trying a new material.
Not to walk away and they come back and say, "Oh, why did it fail?"
Right. So I'm going to go through some of the new materials. Nylons are really attractive for this process, but it's a semi-crystalline material. The ABS is amorphous, so it really complicates. There's some shrinkage. There's definitely shrinkage with all the materials as they cool. So that tends to distort the part, and with depending on the type of polyamide, it can, some are better than others. But we tested carbon fiber and glass fiber reinforced with 0 to 40% fiber. And with hybrids also carbon and glass. So carbon is a fairly expensive fiber compared to glass. If you can replace some of that carbon with glass and still get the properties you need, it lowers the cost of it. And then the mineral fillers are also really important in the nylons. So we work very closely with BASF. Sabic is another material supplier. They work really closely with us. They were the original supplier of the ABS. They also specialize in the PPO material, which is very interesting for chemical resistance. Polycarbonate has turned out to be a really attractive material as well, carbon fiber reinforced polycarbonate, and then some blends. Techmer's a local company from Clinton, Tennessee, and it's really good to work with them because they'll do specialty compounding for us, so we can actually direct, we want to use this type of fiber and in this combination, and so they've been working with us on all types of the materials. And then Eastman is another Tennessee company, and their specialty is copolyesters. And the copolyester is interesting because it doesn't require the reinforcement to print. It doesn't distort, so you can have these clear materials. They can be colored, and I see a lot of application for this, like for architecture, like you can print chandeliers or things like that. Also, some other just smaller companies. We just tested like a few samples from Tajin and Poly1 and this compostable polymers from Algix. This just sort of just shows the types of the tensile tests that we do. We'll plane the material so it has these bumps, and we just run it through a surface planer to smooth it out, and then route the dog bone shapes and use an extensometer for strain measurement. So I'm going to walk through. Here's the improvements in properties. So this is the stress strain curve for the original carbon fiber ABS material. And then here's the carbon fiber polycarbonate. So it has about the same stiffness, but double the strength. So it gets a higher strain to failure. Then this is a nylon that prints well. And so it's about twice the strength of the carbon fiber ABS, or 2.5 times. And then we have one nylon. I'm going the wrong way. Now this is a nylon that's almost 3.5 times the original carbon fiber ABS. And we would really like to get this material to print well. It doesn't print very well yet, but we're trying to work with the manufacturer and get that material to work well. Some of the studies, I mentioned rheology. So in this process, the viscosity of the material is very important. So the viscosity is a function of shear rate, determines how it behaves in the extruder. So we're comparing all these different materials with rheology, and this one just shows the ABS, the virgin ABS versus recycled. So when it goes recycled, it shortens the fibers and it reduces the viscosity. So it just sort of shows the viscosity profile after it's recycled. So I mentioned the time between layers, and so this was when you're using the IR camera to measure that surface temperature during printing. There's it shows surface temperature as a function of time. So the parts are cooling, but it varies. So one's a single bead wall versus a double bead wall. So it gives you basically more time before that layer drops below the glass transition temperature of the polymer. And so that once it drops below the glass transition temperature, that's where we see the strength really drop off. So that's the second plot, is really shows how that Z strength drops off after the temperature drops below the glass transition. This is an old one. This is one of the first things we did at Oak Ridge was this bead overlap. There's a setting in the machine that basically just sets how much, where it sets the next bead in the slicer, so that there's like a little bit of an overlap between the beads, and it just shows sort of the optimum overlap was about 10%. So testing there in the Y, that's the Y direction. So now, fundamental understanding of printability. So one thing, originally we started measuring just we would print a straight bar and then measure how much it would lift. Just the lifting of that bar is a measure of dimensional stability. Then we noticed that the hexagons that we were printing actually lifted as well. So we would started measuring the hexagons. Then the bead width consistency, so that became a real problem with some of the new materials. They would, as you would go, this extruder would speed up and slow down, that bead width would vary, or even just in a constant straight line print. Some of the materials did not behave as well as others as far as that bead width. And so we found some ways to try to help that, adjusting the temperature profile. There's a back pressure adjustment in the extruder that seemed to help with some materials. And then also some things that happen with starts and stops. Some materials will form stringers or gaps. So also some photos of that. But we really need to develop this sort of standard terminology for these phenomenon and some qualitative evaluation methods. The bead thinning, so it's kind of hard to see in the slide, but when you measure this, you can see how as it goes it slows down going into a corner, so the bead tends to thicken, and then as it accelerates out of the corner, it thins again. And so there's some settings in the machine. Spindle derivative gain is sort of what it's called, but you can tweak that a little bit to try to calibrate it. And they're trying to add to the machine to make the machine actually self-calibrate by measuring this width, but that's not implemented yet. And then, so this shows a print gap, and that's really catastrophic. In this one, it was due to the manufacturer just adding some lubricant to the material to try to improve the rheology, the viscosity of it, but it didn't stick as well. So it tended to it just pulled off. Like if it goes around a corner, if it has insufficient tack, doesn't stick, it can pull off. And then once that happens at one layer, the next layer doesn't have anything to attach to, and it just continues around. We went ahead and finished this print because we can still do testing on the other walls, but that one wall was not good. This just shows the corner lift in the hexagon. Not very much, but it's enough to have to compensate for it in the design. This shows the stringers. This is the amphora material from Eastman. It's the polyester, and it just, this isn't really a problem. You can trim it off, but it's something to look out for in the material. Slumping. So some materials retain heat more than others. It's like the thermal conductivity is different, or emissivity is different. And with polycarbonate especially, this was like we tried to print the same design that we printed with other materials, and it just was too soft, and it slumped over. So that could be two layer. You just increase the layer time then, or you may not be able to print as much of an overhang. So typically you can print over a 45-degree overhang angle with most materials. So then we came up with this tool test print. So we sort of had a design of a windshield mold to thermal form a windshield to half of that, and then we added some features to sort of give us a variety of typical features for a tool. And then with each new material, then we started printing this test print, and then we would scan it after it was printed. And then we could show the deviation of the print from the original design, and that's sort of what this shows. And we're collecting all that data now, and then we're working with some simulation partners that are working on, they're developing simulations of the process that try to predict that residual stress and deflection of parts. So this is going to be valuable data to validate those models. So now I'm getting into the structural subcomponent testing. So most of this was done with carbon fiber ABS, but the intent here is to generate data that we can use to validate finite element models of complex shaped parts. So our thought was we want to start doing more complex shapes and understand how the material behaves. We devised this 1 foot by 3 foot box shape outer dimension, and we're loading it in torsion, shear, and bending. So we built this test rig that has torsion, shear, and bending fixtures built into it. It just uses hand jacks, but it has load cells and linear LVDT, like for displacement measurement. And also we use digital image correlation to determine the strain, the full field strain of the specimen during the test. And the types of geometries, so we did like increasing wall thickness, vertical prints versus flat prints, increasing densities of infill, some different manual infill patterns, and then various surface textures. I'll show some photos of that, and then the reinforcement method. So the overwrap method, filling it with foam, and things like that. We actually inserted steel bars in some samples too. That was another way to improve we really want to communicate to the designers the different possibilities for designing structures using 3D printing, and so this was part of that. So we completed about 34 different box designs for 102 individual tests. We used aluminum boxes as a baseline chip. So we also had some aluminum, but foam filled and just hollow welded. These show the different infill patterns, and this is again these are sort of the manual infill patterns. So these are hidden in the box, but this chevron type box, I'll show you this. I've got some details of that. This just shows the overwrap process again, and so this is sort of what that data looks like. This is the chevron infill box in 4-point loading. So this is the full field strain measurement, and this is the Z direction displacement on the left, and then the first principal strain, the surface strains on the right. So you can kind of see the effect of that infill underneath the surface resolving as a difference in surface strain. And so we've just started to do finite element analysis and getting some correlation with this data. But we collected this data on all 102 tests, and really for our phase 1, we were going to do the testing, and then phase 2 is really the simulation effort. And this is just the guy.
It does. It looks like cotton steel the way it stresses.
Yeah, it's fairly linear. So that was just slow-mo of one of the boxes. That's the box that you just saw in the photo there. So it was fun to do all that. The speckle pattern there, that's basically the digital image correlation you just paint a speckle pattern on the surface, and then 2 cameras, and then the computer resolves the strains from that data.
How light is this compared to steel?
Well, the average, so this is it averages about 1.5 grams per cc, and steel is about is 12 grams per cc, something like that. So, I mean, if you can't really compare the density, I did show the specific strength. If you compare it on a, like I showed the fatigue data on a specific basis, so that's normalized for weight, and it compares fairly well to steel when you normalize it for mass. There we go. So this is just one of the original plots we made of this data. It shows the stiffness as a function of weight, and then comparing the different box designs. And then we just wrote a paper for the American Society of Composites, and we produced this plot. It's an Ashby type plot. It's typically used for materials selection. And then we're grouped the different types of boxes and just showing specific stiffness as a function of specific strength, so that, you know, higher performance stuff is up to the upper right. And the aluminum really performed really well. The overwrap boxes also performed well. What was really interesting was the different shapes, and then what performed better in bending versus torsion. And you know, I think it's going to be interesting when we start, you know, designing full structures, that how it behaves. This is just the torsion going through the same things, showing the shear strain on the surface during the torsion tests. And it's not, the torsion of a box is not really ideal for torsion, but, you know, one of the lead designers is a race car driver, and so he, you know, that's all they think about is like torsional rigidity of the frame. And we do expect a lot of beam type structures, so I think it is, you know, it is an appropriate test for this. These are just the results in torsion for some of the boxes, and then here's the Ashby chart in torsion. And here the overwrap did really well, as long as you take aluminum off. Aluminum also did really well. This little inset shows where the aluminum was. So it was interesting to see that. There's just starting to do some simulations. We got our hands on some.
So why did you use aluminum as your test?
Well, as a baseline comparison, well, with the race car designer, lead design, you know, design lead, he was like, well, we need to compare it to aluminum so that we have an isotropic material that we can model in the same configuration. So by using an isotropic material and comparing it to this, you know, this is an anisotropic material. So in order to validate that the model is working well, you can model the aluminum one and say, okay, so are my model is working for aluminum. How does it work for this, you know, complex shape of anisotropic material? And so here's some of the results actually comparing the DIC strain measurement to FEA results, and at different stress levels. So it's that same bending test we were looking at, and then the FEA result below and the DIC result above, and we really did have very good correlation on the, you know, comparing those surface strains. And so then we're I guess I'm showing now we're applying that to the full 3D printed Olli structure. So this is just a real quick, like over the weekend, I did this simulation. This is a rollover, was just applying a 45-degree, like a 7,000 pound distributed load sort of on that corner. And then the gold arrows are just, they're automatic surface or contact pairing. So there's actually bonded composite corner sections connecting the upper and lower printed chassis, and then aluminum tubes. There are 4 aluminum tubes in the center. And so it actually, this was just really a quick check to see, hey, it's going to hold together. It has a chance of passing rollover, and it did pretty well. But it's by no means a complete, stress analysis. And then this is the torsion, so I'm applying 6,000 pounds on each front corner and just constraining the back section there. And then that also had a really, more than adequate torsional rigidity for driving loads.
Is that an exaggerated view?
Yeah, the distortion there is highly exaggerated. It's actually, and this is without windows, or there's some steel or handrails that also provide structural support. This is like a maximum deflection of 9 millimeters. So over.
It looks like half a meter to 9 millimeters.
Yeah.
Yeah, that's just the way the site.
It's just exaggerated, as you can see.
So you can see the shape. Yeah, I should mention that. And that's typical. And then so these are bonded parts. So this is the gluing stress in those contact pairs, just to check to make sure that it's not going to pull apart.
So when you add those bonding elements, how does that affect the recyclability of it?
Well, yeah, that's a good question. So, it depends on the type of adhesive that we use. We're really interested in welding. So these are thermoplastic polymers that can be welded. So we're looking into ultrasonic welding, friction welding, and chemical welding of the thermoplastics. Ideally, we would want to weld it. There are also some newer types of reversible adhesives that they use either induction heating or microwave type heating that will enable you to disassemble parts. And so we're very interested in that. We use an acrylic in most of the cases here, which in that case we would have to cut out the adhesive and not recycle it. So but we're working on that. And this just shows the harmonic. So this is a modal analysis as well. You kind of got a hint of what the 3D printed design looks like, and this is really the presentation that we made after we made the design, and we were trying to sell it to management to get the money to actually build one, which we did. So the concept was that, we were looking at the Olli design, and it has this large beam across the back wall. We thought that's a good beefy structure. We built on that as well as. But there was a problem, it won't print a horizontal space. So we came up with a solution to that, which was to pre-print the support structure. So this red box is the support structure that we printed, printed upside down before we printed the Olli. And so then you print up to that level and then drop the support structure in. It has a little release material on it. And then you can print over top of it so you can get a horizontal surface. And so there was a second one as well. The yellow one was the second one that we put in when it printed up to that level.
Why do that and not just print the support material?
Well, one is you have to machine it away. It's really, it can be difficult to remove it. And that's also extra material that you have to print. And it's also print time. So print time is critical. So to minimize the print time, you can use this type of support structure.
So you just reuse the support?
Yes. We just print them once and then we can reuse them.
So does somebody have to monitor it until it's at that level?
Yeah.
Does the machine automatically stop and wait for somebody to come and do it?
Yeah, we're always, somebody's operating the machine at all times. So, and then we also know the layer time and the print time, so we can estimate when, we have to be ready to drop that part in. So this just shows the design in 2 printed parts, the lower chassis and the upper chassis. There's just some features with the design, like electronic componentry can go in these little areas, and cable throughways and things like that. We had some these little diamonds for lightweighting, and then we decided to just machine those out rather than printing them in. We printed them in, of course. We printed a quarter size one first, and just decided to machine them later. This is the upper section, and this is the sort of what the slicer looks like when you we got the lower chassis is about a 24-hour print, and the upper chassis is a 7-hour print. Let's see. Then the corners are actually molded composite. We 3D print the molds, so we're able to produce molds for composites in about 2 days using this process, and that's a lot of people going into large-scale 3D printing are going into molding. There's even companies starting up that's all they do is they bought a printer just to make composite molds. It has a floor section and a battery rail. So it's just sort of that design. The battery fits underneath, and there's a honeycomb floor. This is the aluminum handrail. So they're actually pretty beefy, and they add some to the structure, almost like a roll cage with those. And then this was just the original, the first analysis of that. Now this is the machining operation. So this is in Mastercam. He estimated the mill time to smooth, to sort of face the surfaces, about 2 hours for the lower chassis, 2 hours for the upper chassis. And there's actually a lot of machining on the front and back faces. So comparing it by weight, that's the biggest question. Is like, oh, it's going to be a lot heavier. And this is our prototype design that's driving today. Comparing the weight of that to the print design, it weighs about the same. It really is about the same weight. But looking at the complexity, this is the prototype design. So it has this aluminum chassis, thousands of parts that are welded together. We use 3D printed molds for thermoformed ABS interior panels. So there's a ton of different interior panels, and then exterior composite panels. And then we do have 3D printed parts in that. So this shows the 3D printed parts in green for the component version of Olli. But then comparing the assembly time now versus that prototype design compared to this 3D printed design is really simple. We originally estimated like 4 man hours, just like bond all these parts together. It's more like 10 or 20, but we do think that it's much less than that original prototype design, and just results in lower costs. I don't have the cost chart on here, but Brad mentioned a little bit about that. And this is just shows the interior, and that's really all that I have. So I'll take any questions. Thank you.
Did you get a crash test?
No, not yet. So this is a low-speed electric vehicle. So that was one of the reasons why we're really focusing on this product for now, is that for a low-speed electric vehicle, we're not required to pass any crash tests.
What speed is that?
25, up to 25. The printed Olli? Well, we're estimating about $8,000 to $10,000.
What does it cost for the machine? One machine takes 24 hours. You only print 365 machines.
Yeah, the machine time is about
So it's 24 hours.
yeah, it's a 24-hour print. So
One machine, 1 day, 365 a year. So I guess you think if the machine costs $1 million, it's $1 million. I'm thinking wrong. So in the design world, what comes first with you guys, the design or the 3D printability?
what comes first, the design or the printability?
Yeah, when you're trying to put a part together, are you thinking, is this going to print, or are you thinking,
Or we'll figure out.
Well, it depends on the design. Look, like, I think the designer really needs to be familiar with the process, the limitations of the machine, and the property variations. That's part of the reason why we did these structural testing, was try to educate the designer the effect of the direction on the properties, and really designers need to get their hands on a machine, or at least see what the machine's capable of and what its limitations are. The guy that designed this has been working with us for 2.5 years, so he's familiar with the machine, what the slicer can do. That's another big aspect of design, is you have to design it so it's sliceable. And there was a lot of the time in that actual design was geared towards making it so the machine can print it and slice it. So I think it's both. It's definitely have to know what I think you have to know what the machine will do before you design. Otherwise, you'll have to make so many changes to it just to make it printable. It's better if you have a really good familiarity with the process and what it can do, what it can't do, what the properties are, and then do the design geared towards the process.
Is there a 3D technology on the horizon that you guys are excited about, that you think might change the story?
Well, we're using a Cincinnati machine now, and there's another company that makes a machine that does some things a little bit differently. It adds a melt pump to the extruder that more precisely meters the flow, and then it also has a roller that follows the print and sort of squeezes it down and presses it. And we're really interested in that machine. So I would say, yeah, there's some improvements in the machine space that we're very interested and excited about, that solve a lot of the problems that we're having today.
Can you reveal your nozzle size or bead width or layer height?
Yeah, well, we typically are using a 0.2 or 0.3 inch nozzle, and that gives us we usually go to like a 0.1 inch layer height and about a 0.5 inch bead width, like a 0.35 to 0.5.
It's all in inches, huh?
Well, I mean, we're working in inches right now.
That's curious, because everywhere else, I mean, in the hobby area, it's all millimeters.
Is it? Yeah, yeah. And I think that's just the way the Oak Ridge machine was first sort of. They were going in those sizes, and we stuck with that. So.
Have you looked at laser bonding and shape the powder bonded the lasers?
So SLS process is very interesting. So you're talking about selective laser sintering with thermoplastic powders, and the scalability of that is the problem. So if we want to build a full vehicle structure, you need like a swimming pool size bed of powder, and that's just no one's gone there yet. It's just a problem with scalability of that process to large scale.
Not to mention vacuum.
Yeah.
For those.
Yeah.
So for laser sintering, you also need pretty low oxygen content when you're making these parts. So most of the time, it's usually like 10⁻⁴ vacuum levels, so like low level vacuum. So that's why so at least at ORNL, some of the metal parts and stuff we do on the metal side, but similar on the lasers on the plastic side, just the vacuum chamber that you need to do it is also like a big limiter. Not only just the powder side, but also maintaining that type of vacuum volume is also like just as you add square feet, just keep adding zeros to the dollar sign of what you want to do that. That's no issue with that.
Have you settled on a final material for doing the trolley? I know you have lots of choices there. Are you going to leave that up to a future designer to pick one that's appropriate?
Well, we're very close to selecting a design or material now. So we're scheduled to down select the 3. So but we haven't yet. So it's still open. It's just because the material suppliers are improving everything, you know, and we're having so much fun testing new materials. It's like we don't want to pick one yet, but we have to. I mean, we have to settle on one. But we have a lot of options now. So,
how much of a limiting factor is the temperature ranges of the plastic you're using as far as the environments that you want to use the olives? Like, you know,
well, they're all acceptable for the automotive use temperature range. I mean, for, you know,
I mean, as far as like on the really, really damn hot days, are you gonna have to worry about that material softening up on it?
that's definitely something we're looking at. So some of the nylons do have lower, say a lower softening point than the, say, polycarbonate, for instance, gives you about 10 degrees C better temperature performance as compared to the ABS. So that's one of the reasons why I'm kind of leaning towards polycarbonate. Polycarbonate also gives you inherent flame resistance and its moisture impermeability. So if I had to place my bets now, I mean, there are some nylons that are better than others, but the polycarbonate is, it's basically between polycarbonate and nylon-based materials right now. Polycarbonate prints really well, so we'll see.
And always some fiber in it. Is that a given?
Yeah, except for the polyesters, but polyesters are really low modulus. It's not really a structural material as much as the carbon fiber reinforced stuff. But what the carbon fiber does, and there's been papers on this, but if you just print pure ABS, it just curls up, like, it shrinks a lot. And the carbon fiber has a negative CTE, so it sort of cancels that out. So that when you put the carbon fiber in there, it really enables the process.
Mm-hmm. So now that you got the material as light as possible, and you got the batteries in the car, and you got the people there, you got air conditioning going, how long will the battery last before you have to recharge? Is it once a day, or is it once every hour?
Well, that's a question for Billy. He's our powertrain guy.
Currently, we're getting about 60 hours of the battery pack. But what we're planning on doing is using with the Oak Ridge National Lab is wireless charging. So we're going to have docking stations because we don't want a human to have to plug in an autonomous vehicle.
And that's with air conditioning as well? Because
yes, yeah. And
60 hours?
Yeah, and we'll also be able to get health monitoring status at the docking stations. So the vehicle will have intelligence, so it'll know when it needs to go charge. It'll go charge, download the health monitoring status of the vehicle. That's the strategy.
Is that using regenerative braking?
Yes. Yeah. The duty cycles.
On the streets, I gotta see what these things driving around. Years, decades.
I guess we're probably looking at, the pilot programs we're looking at next year, obviously. But, from a real world commercial type application, probably looking more like 24 months.
A couple of years.
Yeah.
Who do you think your first customers will be?
Well, we have a lot of research labs and universities that'll be our first customers.
There's no seatbelts in there, are there?
That's correct, no seatbelts.
this is most good you.
Yeah.
I don't care.
I want. It's actually I've done speed studies. I've done some speed studies with the vehicle at 25 miles an hour. People are very comfortable and intuitive and talking to Watson and Alexa and all the other stuff.
Buses and subways don't have seatbelts.
They're a lot heavier too.
So the engineering requirements change. You have two of these things run into each other. So regular car is only thing holds up in plastic parts. But you get two of these things hit each other at high speed. The engineering requirements change.
So for crash performance, we would design specific structures that would absorb the crash. And so you would design it for, and that's one of the things that the crash requirement is this, it has to have some kind of give. That's why you have like the crumple zone in the car. So we would design in that sort of crumple zone to absorb the energy of the crash. So that's one thing that we think that this additive manufacturing process does, is it gives us a lot of flexibility in designing that sort of crash structure. But I think you're going to have the same effect two of these hit each other versus a car hitting one. It's, there's not much difference there. But I mean, these are low speed, so starting out with a low speed application really gives us time to develop that crash performance. We do have plans in our phase 2 IACME project to do crush tests. So Oak Ridge has this test machine for automotive crash worthiness. It does a constant velocity crush test. So we're going to collect data on the materials with that machine, and then do some simulation, some crash simulation with that data, and try to predict how it'll perform and develop some preliminary designs for highway applications.
You got golf carts that are illegal to drive on the streets, and they're only asking for the same restrictions.
I'm really curious about your chemical welding technologies here, because you print a part for 24 hours and it screws up on like the top bracket. Can you go in and weld a little mount plate there or something, or is it just recycle, you melt it down and start over again?
Well, I mean, we have both those options. We haven't done much repairing, but that we think that's a possibility. You could repair and rework parts.
Are these welds like metal welds where the weld's actually stronger than the material itself?
We haven't done enough testing to say that. One thing is, this is fiber reinforced, so how that weld, how the fibers aligned in that weld will affect its properties. So that's just future work to determine those types of things.
Question about competitor.
What's that again?
A question about, like I read an article, they are doing a self-driving similar kind of thing in University of Michigan, MCT, and the company name is Navia, French-based.
Mm-hmm.
So where do you see yourself in terms of competitors in the same market?
Do you want to answer that one? Or?
Well, I mean, it's more of an answer for Brad from that side of the business.
Yeah.
We're just engineers, so.
Yeah, they're definitely a competitor
Yeah, I mean,
of ours. I mean,
yeah.
they're in production now. They've produced hundreds of vehicles. So yeah, they're a competitor, and that's about all I can say
I mean,
about that.
it's like if you think about the market itself, right now it's such a small market anyway. So it's like we're competing against each other. That we're competing to get the mobility out to the cities. So there's just getting people to understand that all these even for me as a a car guy and a bike guy, it took me having going out and demonstrating Olli to realize that Olli's purpose is for my daughter and for my mother, and eventually for me, in a sense of being able to have that mobility freedom for my mother. She's driving less and less every day, and then my daughter, who I don't want to drive. So from that perspective, the generation of instead we all used to look for our car keys when we get up in the morning. Now we look for our brains. So to have that convenience of and consider it an Uber without a driver. So that's basically the application. So from that perspective. Yeah.
Infrastructure security is becoming a big news item, a big kind of concern. So is that already in your awareness of someone hacking the?
Absolutely. We talk about being able to do, to download software, on the fly and things like that.
How you push an update? How you trust?
Yes, yeah. So there's a lot of with recent activity, in the news that we all know about, and there's a lot of conversation. I've actually been contacted by several government agencies about that. Everyone's concerned about it, but once again, we're all fighting the same fight. So it's going to really be interesting to see, even when you look at Tesla and the way they're updating their software. So things like that are going to come into concern, because that, for them, it's a potential. There's a potential with everything like that. So we're definitely looking into that.
Yeah.
Okay.
What protects you from the competition? I mean, you're laying out a lot of data here, you're just doing to the general public here. Is it more you're protection is in the software than it is in the hardware as a company. Like the Chinese to pick this up and do it themselves now.
Yeah,
write it all out for them.
You know, I mean, we're open source co-creation, and you know that's our thing is like to get it out there because we're not. You know, our goal at the end of the day is not to just build Ollies. You know, it's to give Ollie out there and let someone commercially take it and build it, and then we go on to the next thing.
Oh, so you more research and build?
Yeah.
So that means you need to be making money at this stage of the game, right?
Yes,
If
absolutely.
you're in that, you said you were in that, I don't remember what the term was you used, but that in between that, you know, pre-market kind of a niche where 1,000 vehicles is where you want to be.
Yep.
And once it becomes popular where, you know, we're making hundreds of thousands, you're out of the game.
Yep.
Yeah.
Interesting.
All right, let's thank these guys again for coming in and this presentation. Thanks for thanks again, everybody, for coming out tonight. So for KnoxData, our next meetup will be next month, and we'll be talking a little bit about the Python. We'll be doing some image learning tutorials for guys here. And also, I want to give a plug. I didn't give a plug when I started. So KnoxDevs, the umbrella group for all the developer networks communities here in Knoxville, we're doing a quarterly meetup next month in the Sunsphere. That'll be the second Thursday.
10th.
The 10th, okay, yes, I thought, yeah. So August 10th, you can sign up on Meetup. Go to meetup.com/KnoxDevs. You can find the quarterly meetup thing there. What we're going to do is on the third, whatever floor, yeah, that will be on, that we direct people to. We're going to have kind of a roundabout way in the Sunsphere where you can meet all the different meetups that are in Knoxville, developer related here. So both data science, 3D printing will be there. And you be kind of a one-on-one chat. We'll have drinks available there as well as some snacks and food and some of that kind of stuff. And you can meet all the different people in Knoxville related to that. So should expect about 90, 100 people or so coming out for it. So we have a couple startups as well that might be there as well. So so stay tuned for that. And I'll update people through the meetup when our next Knox3DP meetup will be. We're still figuring out speaker and stuff for that. So
Is that going to be a matrix?
yes. So yeah. So so some people who came in late. This was kind of a partnership between two different meetups. So data science meetup that meets here every third Thursday of every month here in the Tech Co-op, as well as Knox3DP, a 3D printing meetup group for people interested in CAD, 3D printing, a lot of more stuff on the hobbyist side, but also stuff like this, bringing in some industry perspective as well. We generally meet the first Wednesday of every month at Knox Makers, which is just south of the river here. It's really good space. So yeah, we'll be doing that in the future. So thanks for coming out.